Hello everyone, I'm Suli Yao from the Chinese University of Hong Kong, and it's my great honor to have the chance to share with you about my recent work focusing on the seismic hazard assessment and ground motion predictions based on the interseismic logging models. Ground motion prediction is a very critical element in seismic hazard assessment, and it is usually conducted by using the ground motion prediction equation that are derived from the ground motion record and describe how the ground motion intensity decay with the epicenter distance. However, such methods usually suffer from the lack of the near field data. And to fill in this gap, we can use other methods such as the dynamic rupture simulations to simulate the ground motions in the near fault region. And such dynamic rupture models are well known to highly depend on the model inputs such as the fault structure and also the initial stress on the fault. But due to the lack of the direct measurements of the fault stress, we usually assume it to be uniform or depth dependent or stochastic in dynamic rupture models. And in our study, we intend to use the interseismic logging models as the constraint on the fault stress. The logging model describes the distribution of the slip deficit accumulation on the fault during the interseismic periods. And those highly locked regions are anticipated to hold significant fault slip during the future earthquakes, and thus may feature higher earthquake potential. Our study region is the Mid-American subduction zone in Nicoya, where the Cocos Plate subducts beneath the Caribbean Plate. There is a very dense geodetic and seismic observation network installed on the Nicoya Peninsula. And based on those geodetic observations, there are two logging models for this megathrust. And from this map view, we can see the great consistency between the two logging models. With some slight differences in details. And in the 2012, there was a magnitude 7.6 megathrust earthquake ruptured on this fault with a very large overlap with the logging models. So the extensive near-field observations in this region actually offer a very good opportunity for us to investigate the link between the coseismic rupture and the interseismic logging. And what we want to do is that we want to derive the rupture scenarios from the logging models and also the ground motion predictions in those scenarios. And then we compare our predictions with the observations during the 2012 events to validate our predictions, and then to investigate the potential application of logging models in hazard assessment. The first step we take is to estimate the initial stress based on the logging degree distribution, and then the initial stress is utilized as the input for the spontaneous rupture simulation. Here I show you a case. We nucleate the rupture from the hypocenter of the 2012 events, and then we conduct spontaneous rupture simulation to get this scenario. And we find that the final rupture extent, magnitude, and the moment rate function in this scenario are similar to the 2012 events, which indicate the potential of predicting future earthquake from the logging model. However, the question is that we actually do not know about the future earthquake hypocenter before its occurrence. And our simulation results indicates that even with the same initial stress distribution, the different hypocenter locations may lead to totally different rupture scenarios. For example, if the rupture starts from the blue star here, it will lead to a breakaway rupture and finally result in a moment magnitude 7.4 earthquake. But if the rupture initiates from the red star just neighboring to this one, it will only result in a very small event with magnitude 5.7, which we turn it in as the self-arresting case. And we test a sort of different nucleation sites in the locked region, as denoted by those circles. And the color for each circle indicates the final moment magnitude for each scenario. We find that the ruptures that initiated from the highly locked region have higher potential to grow into a large earthquakes. And among those scenarios that derive from Feng's locking model, 29 of them eventually turn into breakaway ruptures and break the whole locked patch with moment magnitude around 7.5. And those color curves indicate the rupture extent of those scenarios. So despite some small differences in the offshore patch, those scenarios are actually confined in the highly locked region. Those blue triangles indicate the locations of the local high-rate GPS and strong motion stations that are used in the prediction validation later. Even with the very similar rupture extent and moment magnitudes, different hypocenter locations can lead to different rupture process and thus may impact the ground motion intensity. So here we compare the synthetic ground motions on this station in the 4 scenarios with different nucleation sites. And we found that the scenario in parallel A, which nucleate offshore and propagate towards the station, actually result in the strongest ground motion intensity on these stations, comparing to the other 3 ones, due to the rupture directivity towards the station. Then we generate the predictions for ground motion intensity measures, including the peak ground velocity, peak ground acceleration, and displacement on the near-field stations. Since we want to capture the high-risk ground shaking in this region, so we only consider those breakaway ruptures. And because we do not know about the hypocenter in future earthquakes, so we treat each scenario equally in the calculation. And then we compare the prediction with the 2012 events that's denoted as the blue stars in this figure. And we found that actually most of the measurements are captured by the prediction within 1 standard deviation. The light blue and the gray lines indicate the average values among all the stations, and we in the observation and the prediction, and we can find the great consistency between the 2 values. Please note that we have applied low pass band filters to the waveforms before picking the PGV and the PGA. We also compare our predictions and observations in the spectral domain and find a great consistency in the frequency band from 0.02 to 0.5 Hertz. For the higher frequency, because we applied a very simple 1D layered velocity model and the lack of heterogeneities in smaller scales for the structure, so the high frequency energy, like over 0.5 Hertz, is inadequate in our model. So that is why we need to apply a low pass filter before we picking the PGV and the PGA. And the story is a little bit different in another locking model. So based on the Scher's locking model, we only have seven scenarios that eventually break the whole patch and are resulting in the magnitude like 7.4 to 7.5 something. And instead, we have some other scenarios that confined on the offshore or confined on the onshore patch and terminate at the gap between. That is because at the gap, the locking degree is very low. And such low locked region may impede the rupture propagation and forming such rupture segmentation phenomenon. And due to the smaller moment magnitudes, those moment magnitude 7.2 events actually predict the ground motion intensity lower than those 7.5 events by 30 to 40%. So in summary, we derived the rupture scenarios and the ground motion predictions from the locking models by considering different nucleation sites. And then we compare our predictions with the observations during the 2012 events and found that the prediction in our breakaway rupture scenarios with moment magnitude around 7.5 actually fit the observations in the low frequencies, which may indicate the potential application of the locking models in seismic hazard assessment. Furthermore, we also observed the rupture segmentations in the rupture scenario derived from stress locking model, which may indicate the dependency of the prediction on the locking model resolution, and highlights the potential challenge of predicting future earthquake magnitude and ground motion from locking models. And that's all my presentation. Thank you for listening.